Okay, thank you everybody for attending. Today's topic on the EPA's Small Drinking Water Systems webinar series is Tribal and Very Small Systems. Welcome and thank you for attending, and I will pass it off to Michelle to handle a little bit of logistics before we get going.
All right, thanks, Tom. Just a couple things before we get started and Tom introduces the speakers. We do offer a certificate for a continuing education contact hour. If you're registered, you will get a certificate if you said that you wanted one during registration. If you change your mind and you want one, go ahead and put that in the questions box. And also, actually, I'll go over certificates here in a minute on the next slide. Just a couple things before we go there. You do have the handouts. The slides are emailed to you, but they're also in the handout drop down on your navigation bar. So if you'd like a copy of the slides, they're there for you. And we will have a Q&A session at the end of the webinar. So feel free to type a question anytime for the presenters in the questions box. We'll get to those at the end of both talks. And also, if you have a question about anything else, if you're having audio issues or any other questions, feel free to type those there. Okay, next slide, Tom, if you could. So for the certificates, you have to attend the live webinar, and you have to attend for 30 minutes in order to receive the certificate. If you're in a room with someone else and you would like a certificate, you're not logged in, the person who is logged in can send us those names. You can either type the names in the questions box, or you can send it to this email address you see here in number 3. And also, we did forget to mention before we get started, if you've just joined us and didn't take the poll, if you have more than one person in the room with you, if you could type that in the questions box for us, it really helps us with our outreach efforts. And that's only if you have more than one person in the room with you. And just to let you know some upcoming webinars that we have actually one tomorrow on PFAS, and this is methods and guidance for sampling and analyzing for PFAS, and this includes drinking water. So if you're interested, registration's open, and that's tomorrow from 2 to 3. And for our small systems webinar series, which you've joined right now, we actually are not going to have a December webinar this year, but we already have January planned, and it is treatment technologies for removing chemicals of concern. And this includes PFAS, cyanotoxins, and what is it, 1,4?
Nitrate, 1,4-dioxane.
Yeah, 1,4-dioxane. So registration will be up for that soon. It's not up yet, but it will be available soon. And with that, Tom, I think we're good. I'll turn it to you.
Okay, great. So this slide is just our normal EPA disclaimer, and we'll go right into our talks. So our first speaker is Marlia LaBelle. Marlia is a tribal member of the Native Village of Port Graham. She is a project manager with the National Tribal Water Center, a program of the Alaskan Native Tribal Health Consortium. She assists with program development and provides technical assistance for Alaska, Native, and American Indian communities on water and sanitation-related issues. Marlia has an MA in Rural Development from the University of Alaska Fairbanks. She joined the Alaska Native Tribal Health Consortium in 2015 as a project manager for the Alaska Rural Utility Collaborative. Marlia also has 10 years of public relations and communications experience serving Alaska Native organizations. So with that, I'll pass the podium to Marlia.
Good morning. Chamai, Uvlalutak, Uvanga, Adiga, Marlia, Makbiak Label. And so I wanted to share with you, I'm just saying good morning. It's morning in Alaska, so I can say good morning. I am Sukbiak and Inupiaq, and I'm a tribal member of the Native Village of Port Graham. My family is from Port Graham and Kotzebue, Alaska. So if you can see my screen, that is me on the left in Kotzebue, where my paternal grandmother is from. And so, yeah, I've been with the National Tribal Water Center for about 2 years now. And so the National Tribal Water Center is a program of the Alaska Native Tribal Health Consortium, also known as ANTHC. And ANTHC is a statewide nonprofit health organization that provides health care for more than 160,000 Alaska Native and American Indian people living in Alaska. So what's unique about ANTHC is that in our healthcare system, Alaska Native people own and manage our own healthcare system. Within ANTHC, we also have an engineering department, project management, construction, and operations and maintenance. Although the National Tribal Water Center is different in that we don't just serve tribes in Alaska, we serve tribes nationwide. And so the Water Center was created to help fill the gaps in the traditional service delivery model. And I'll explain what those gaps are on the next slide. Let's see. There we go. So in order to give some background and context about how the National Tribal Water Center works with tribes, I just wanted to convey what the funding need is for Indian country compared to the funding that they receive. So according to the Indian Health Service, there is a construction backlog of some $2.5 billion in water and sanitation construction. And the total need for water and sanitation in Alaska and American Indian communities is over $3 billion. And that number is only going to continue to grow. One of the main reasons that number is so high is because of aging infrastructure. So to put it all into perspective, in FY16, the funding that tribes received for water and sanitation construction was $99 million. So Alaska Native and American Indian communities don't receive adequate funding for water and sanitation. And these are some of the ways that we work with tribes to ensure that they have safe and sustainable water services. So I'll discuss how we partner with tribes in these project areas, and they are traditional and unregulated water sources, outreach and education, and engineering and evaluation. Since we have a limited amount of time, I won't be able to cover everything. So traditional and unregulated water sources. So according to the Indian Health Service, adequate sanitation facilities are lacking in some 145,000 Alaska Native and American Indian homes. And of that number, approximately 26,000 homes lack access to safe water supply and or a wastewater disposal facility. So some of the ways that Native communities kind of bridge this gap is through collecting traditional water, such as water from springs or streams, or collecting rainwater. Another way is private wells. So, and all of these sources are not regulated under the Safe Drinking Water Act. So what we definitely just want to provide the education and information to tribes to ensure that the water that they are using is safe. So we are currently working on 2 unregulated water source projects, and one is with the Cherokee Nation and one is with the Cheyenne tribe. So, and this is a partnership with the tribes and the U.S. Centers for Disease Control and Georgia Tech. We help develop a plan for testing the private wells. In Northern Cheyenne, they collect water from springs. And so this data will help inform a future data collection and contaminant protection. In addition to all that, of the information, all the data that we collect, we also provide education and outreach materials. So when we work with the tribes, we help identify sampling timeframes. if there are particular times a year that there are an increase in contaminants, we want to be able to, capture that information and work with the tribes to create a data management plan. Oftentimes, tribes elect to own and maintain their own data. So, if there are, data from homes and we don't see the names of the people that are associated with that data. Neither does the CDC. It's only the tribe that will own that data. So when we do receive data and we help analyze it, that data is de-identified. And so we also provide outreach and education to homeowners, in case there are exceedances, information on how to maintain and operate their wells and how to treat their water. So this is another way that we work with tribes through outreach and education. Our current projects are the Water is Life, the Our Water Toolkit, and community relations for new water systems in rural Alaska. So this photo here is from a youth art project in Deering, Alaska. You'll see in a sec just how great this project is. So the Water is Life project was created as a way to re-engage communities with water through public art. And so these are some of the project objectives for the Water is Life project: improve sustainability of safe, healthy, local drinking water sources, preserve and share local water culture knowledge, increase knowledge and awareness of the health benefits of water. So there could be any number of reasons that tribes would want to engage the community with water, and these are the ones that we hope that the Water is Life projects help improve. So this is a flow chart of the Water is Life project, and it starts with an idea, someone in the community wanting to improve something about their local water, whether it's use, quality, access, and that idea, will turn into a proposal to pursue funding. And then identifying all of the project partners, the project lead, somebody taking care of communications, somebody from the utility, as well as identifying an artist. So, once everything is in place, you can begin planning the Water is Life project. And the first way that we engage with the community is through a visioning meeting. So we invite everybody in the community to attend with, kind of a special emphasis on culture bearers and elders. And so when everybody is together, we just ask them to share what water means to them. What does it mean, for them culturally? What does it mean for them, in a traditional sense? And so while this is happening, we have an artist attending and listening, and they're taking notes and they're sketching ideas, and then we come back to the community, after a couple of weeks, kind of let all of the information, sink in, and then they'll have a sketch for a mural painting. And so that's what you could see kind of in the middle there. That's from an artist, Andrew Morrison, and he was the first artist actually who helped with the Water is Life project. So we'll come back to the community and we'll do what we call Water Week. And there's a number of activities that we put on, throughout the week in the community, such as water bingo, storytelling, youth murals. We could also, work with the utility, as well as giving tours of the water treatment plant. So, and while all these activities are happening, the artist is painting, a large scale mural on their water storage tank. And at the end of the week, we have a big mural unveiling and celebrate water, celebrate the mural. And, from there, the hope is that the community is engaged and they're thinking about water and talking about water, and, they're re-engaged with their utility. So these are some photos from some of our previous Water is Life projects. We've done 3 in Montana, 2 in Alaska, and we're currently working on finalizing a Water is Life curriculum so that tribes are able to plan and implement their own Water is Life project in their communities. So so we've done them in Deering and Russian Mission, Alaska, the Northern Cheyenne Tribe in Montana, and this last summer we did one with the Blackfeet Nation, and we hope to have the curriculum available for tribes in the late spring or early summer 2019. So, and this is another way that we provide a resource for tribes, and this is actually where the Water is Life curriculum will be a part of once it is available, is on our water toolkit that's available on our website, and that can be found at tribalwater.org. So this toolkit was created for tribally managed utilities, for tribal staff to lead and implement their own water initiatives in their communities. The toolkit has a ton of information on the site and was designed for 3 main audiences: customers, utility staff, and local leadership. This resource is a living, breathing resource. We're constantly making updates and improvements to the site, constantly adding information, and it covers a broad range of information from how to improve the perception and water quality and encourage use to, say, ordinances and governance of utilities. So do you remember how I mentioned that 26,000 Alaska Native and American Indian homes lack access to safe water and sanitation? So of that number, 3,300 are in Alaska. So the National Tribal Water Center partners with our construction and project management to provide community relations for Alaska Native communities that are receiving water service for the first time. So there's many challenges, to access to safe water and sanitation in Alaska. Funding is the main challenge, right? I showed earlier, it's expensive, but it's also challenging in other ways, because so many of our communities are remote. We only have 2 major highways in Alaska. We're heavily dependent on the weather. We also have a very short window for construction. So there's a large amount of work that has to happen. So projects take longer, than they would in the lower 48. So, but community relations is very important when working with tribes. Everybody in a community, they're all, everybody is a part of the community. Everybody cares about the community. Everybody wants to know what's happening in the community. So it's very important when working with tribes that, somebody in the leadership has a seat at the table during project planning, for community support and buy-in of the project. So in addition to holding community meetings where we provide project updates, we also do activities in the schools with kids. So you can see that top photo of that little boy there. We teach, the younger little kids about the water cycle through watercolor painting, and teach older kids about water filtration and water treatment through science experiments. So those are photos from Eco Alaska, and I want to say by summer 2019, the entire village will be connected to the water treatment system. So everybody in the village will have water. And the last main area that the National Tribal Water Center provides service is through research and evaluation. These are some of our current research projects. The Portable Alternative Sanitation System, also known as PASS, Health and Wellbeing Study in Kivalina and Newtok, and a per capita water and fixture use study in rural Alaska. That's me in Kivalina. What has been, very important, when working with the communities is, making sure that they're involved and engaged. And I'll explain that in just a second. But this is the Portable Alternative Sanitation System, also known as PASS. You can see on the left of the photo, there's a rain catchment, which is connected to a water treatment system and water storage tank inside the home. There is a low flow sink where people can wash their hands. There is a waterless urinal. And the reason for that is because the toilet is a separating toilet and you have to sit down to use it. So the liquids go in the front and the solids go in the back. The solid is, the toilet itself is connected to a ventilation system. So the liquids drain into a seepage pit and the solids are dried out by a fan and can be removed by, can take them to the landfill or they could be burned. But this system was created for as a low-cost alternative for communities impacted by climate change and lack water and sanitation. So, there's about 34 communities in Alaska that do not have running water and flushing toilets, meaning they haul water and use honey buckets. So, and we all know that communities who lack water have higher rates of diseases than those that have adequate water and sanitation. So this photo on the left is a model of PASS, and the photo on the right is an actual PASS system in somebody's home in Kivalina. And so the study, I mentioned, the special consideration when working with tribes. We have to go through a number of approvals in order to collect data and interview human subjects and work with communities. So we have to get approval from the tribe. We also have to get approval from their health corporation, as well as our own approval, our own institutional review board here at NTWC. So we're working with the communities, in a much closer way. And we've also done this through the creation of community advisory committees in each community. So there's one in Newtok and there's one in Kivalina. And so these committees review the interview questions. They know and understand the study. They are aware of the methodologies that are being used to collect data. And they're also, when we are collecting data, we've only just started this last fall But as we collect more data, these community advisory committees are also going to help us analyze and interpret the data. So they're going to see what we see, but they're going to maybe give us a little more richer background and fuller understanding of what that data might mean. So the objectives of the study are to measure how past affects household water security. So we're looking at water consumption patterns, water and sanitation related exposures. We're looking at how people use PASS. You know, is it culturally appropriate? Is it easy to use and affordable? So one of the things that people, you know, have to have if they have a PASS system is, you know, it does use a little bit of electricity, particularly in the winter, you know, in order for the water lines to not freeze, but also to engage communities to develop a health outcome study. So, you know, just wanted to close with, you know, that tribes face many challenges in providing water and sanitation for their communities. And we hope that we serve as a bridge for tribes, providing safe and sustainable water. And I'll just close with in Thank you very much.
All right, thank you very much, Marlia. So that concludes our first talk, and as our custom, we will go on to the second talk. We will have questions at the end of the second talk for both speakers. So if you have questions, keep the questions coming in for Marlia, and we'll organize them and we'll ask them at the end of the second talk, which will be at the top of the hour. And then we'll go until about 3:30 Eastern time. So we'll do that. Keep the questions coming into the question box, and that would be great. Also, a little bit of logistics. If you missed the poll, if you didn't do the poll, and you have more than one person in your room watching the webinar, please put that into the question box, how many people are in your room. It helps us document how many people are attending the webinar and justifies the webinar series. That would be great. If it's just you watching the webinar, you don't need to bother. Just for those that have more than one in the room, that would be wonderful. Okay, so we'll, Marlia gave a great first talk. So up next is Craig Patterson. So we can switch to Craig's slide. And Craig is, while they're doing that, I'll give the introduction. So Craig is an environmental engineer with the EPA's Office of Research and Development. He has over 35 years of experience with the federal government programs, environmental programs, and environmental consulting firms. Over the past 15 years, Craig's research emphasis has been on drinking water treatment technologies for small communities of less than 500 people. His research has focused mainly on emerging and innovative water treatment technologies in support of EPA's regulatory requirements, including household water system studies. This effort has included collaborative field studies on a wide variety of surface and groundwater sources with researchers in EPA's regions, states, health departments, water utilities, private industry, tribal entities, and academia. And with that, I'll pass the podium over to Craig.
Well, thank you very much, Tom. Thank you everyone for being here. Today's presentation is a summary of some research studies we've done in Puerto Rico in collaboration with Inter-American University. Since 2009, we started out working in very small communities in the rural areas of Puerto Rico, did some water system improvements, including adding some UV disinfection systems to 2 of the communities, and then doing some studies with the disinfection systems. We did some renewable energy and biosand filter studies in 2015. And then in 2017, we did some citizen science and water quality monitoring studies. And then in September 20th, 2017, Hurricane Maria hit. So this presentation will cover all these separate research studies. For those who don't know where Puerto Rico is, it's southeast of Florida and Cuba, next to Haiti and Dominican Republic. we are working with Inter-American University, the San German campus on the southwest side of the island. The Center for Environmental Education, Conservation, and Research is located at IAU. The systems we're talking about that I'm going to highlight today are on the southeast side of the island. There are 3 communities, Apiadero, La Sofia, and Mulas Hagwal. Apiadero has a conventional treatment system of biosand filters and solar panels that we've installed, and then the Mulas Hagwal has a slow sand filter, and La Sofia has a groundwater source with a sand filter and UV system. Looking at the terrain in Puerto Rico, you can see it's very rugged. These are rural communities up in the mountains, a lot of bamboo and rainforest, and small populations, small subdivisions. The EPA Region 2 has documented some of the issues surrounding non-process water systems. Non-process systems are water systems that are outside the control of Puerto Rico Aqueduct and Sewer Authority, or PRASA, and there are 242 of these water systems. 140 of these systems serve between 100 and 500 people. Only about 76% of these, and 185 of the 242 systems use some form of chlorination, and only 60% report negative bacteriological results. And one of the major issues is only 4% of the systems use filtration technologies. So there's a clear need for a multi-barrier approach to provide safe water and improve health of individuals living in these non-process communities. A typical surface water system is comprised of a dam and a creek up in the mountains with a screened intake leading to a pipe that goes into a tablet chlorinator on top of a water storage tank shown on slide 28. And then slide 29 provides some other pictures of the tablet chlorinators on top of the water storage tanks. The chlorine tablets are replaced, the water flows and dissolves the chlorine tablets and introduces chlorine into the water storage tank. So some of the majority of the violations are for the total coliform rule. There were 1,650 violations in fiscal year 2015 and 182 systems, 136 maximum contaminant level violations in 74 systems, affecting a population of roughly 40,000 people. And the most immediate challenges are getting filtration for the surface water sources, disinfection. There's not enough water during drought seasons, and there's intermittent power, and there's no money to pay for improvements. So what we did in 2009, we focused on 3 of the communities, Apiadero, La Sofia, and Mulas Hagwal. The only community using groundwater was La Sofia. The other communities all 3 communities had water storage tanks with tablet chlorinators, but we wanted to add some filtration. So we looked at slow sand filters, drum sand filters, pressure sand filters, and biosand filters, and also UV disinfection in addition to the tablet chlorinators. And if there wasn't enough water, we tied together water sources and pumped the water. And if there wasn't any power, we installed the solar power. And you know, the no money to pay for improvements, we wanted to work with the communities to show the benefits of clean drinking water to get their buy-in. The La Sofia system shown here in 2014, the local chapter of AWWA fabricated this cabinet where we housed the UV disinfection system shown in the upper right-hand corner of slide 33. We also installed pressure sand pre-filters. The problem here was whenever the groundwater well pump would kick on, turbidity would kick up through the system, and this prevented the turbidity from reaching the UV disinfection system. Here we are installing the pre-filters, community volunteers and operators helping out. And then the Apiadero system was a surface water system. EPA had a package plant, which was roughly $50,000 back in the 1990s that they donated. It was shipped by barge through New York to Puerto Rico, and today's cost, this would be in upwards of about $150,000. So it's not really a low-cost treatment technology, but it definitely was working well for the community of Apiadero. Here we are with the package plant delivered, installing the chemical feed tank, the electricity. The community had installed a platform for the package plant. You can see the backwash water tank, the blue tank on the bottom right-hand slide. Then we added the multimedia filter, which involved hauling these bags up to the very high point in the watershed. And you can see the as-built system at the bottom of slide 38. The final system was a slow sand filter at Mulas Hogwell. Merck Pharmaceutical donated $50,000 for a grant through Inter-American University to install the slow sand filter. These chemical storage bins were used as a roughing filter. Gravel was added to take out a lot of the large particles before they made their way to the slow sand filter. Here's the slow sand filter being built. You can see how mountainous it is. That track hoe is about 400 feet off next to a 400-foot hill. So installing these water systems is no easy task. Here's the system as built with the roughing filter in operation. And the next study is the UV disinfection studies we did in 2013. We installed UV systems at Apiadero and La Sofia. Since there wasn't filtration, it's a good opportunity to knock out chlorine-resistant pathogens like Cryptosporidium and Giardia with very low UV intensity. It's shown here, 4 log removal at 22 millijoules per centimeter squared second. And then the chlorine takes care of the UV-resistant pathogens. So the combination really works well. Here's some of the costs from the UV treatment system at La Sofia. You can see the 45 gallon per minute UV max with the cartridge pre-filters, and then the pressure sand filters. The reason we have 2 there is the first one, the groundwater well pressure was too high and the seals were leaking, so we got a higher pressure sand pre-filter to prevent the system from leaking. And you can also see the replacement parts there, the UV bulbs and UV quartz sleeve. And doing the cost per 1,000 gallons, you can see roughly treating 26 million gallons at 10 gallons per minute over 5 years comes out to roughly $1 per 1,000 gallons. And we have separated the operational costs for a total cost of $27,000. So the evaluation portion of this study was to use MS2 bacteriophage as a surrogate for viruses. We tested 3 flow rates on 2 systems using a collimated beam study that was conducted by BioVir Laboratories on the same MS2 stock and water that was shipped from each site. And then we looked at the UV transmissivity measured on the feed water to the systems. UVT results were very good at the time we did the study. They were all greater than 90%. UV disinfection system manufacturers typically recommend a UVT greater than 70%. Here we are sampling the Apiadero system for raw and treated water and the La Sofia system. For people who haven't been to Puerto Rico, it gets light between 6 and 7 in the morning and dark between 6 and 7 at night year-round because it's closer to the equator. So if you don't get your sampling done, you're going to have to do it by car headlights. And you can see in the middle of the slide there, we're adding the MS2 to the system. As shown here on slide 49, the injection port, and then this influent and effluent sampling ports. This is the collimated beam curve looking at the UV dose compared with log reduction. And here are the results. This is somewhat complicated, so I'll go through it quickly. At the 3, 4, and 5 gallons per minute, we were getting between 4 and 5 log removal. So in summary, Apiadero 7 MS2 viral surrogate studies were performed in September 2013 and April 2014 with UV doses varying between 90 and 120 millijoules per centimeter squared second. And the reason for the high dosage was that we were operating 45 gallon per minute systems at 5 gallons per minute, but they worked like a charm with 5 log removal or 99.99% removal of the viral surrogate. In addition, an effective strategy for training on operation and maintenance of UV treatment system is as important as purchase and installation. I'm going to go through some of the UV port sleeve maintenance. In Puerto Rico, it's very hot and humid, so the biofilm will build up on a monthly basis on the quart sleeve. It's a green biofilm, and biocide is used to clean those quart sleeves to keep the UV light reaching the water. The bulbs burn out typically about every 2 years, and one of our systems is burned out in 6 months. Also, we found that the UV intensity meters also had biofilm buildup, as you can see in the middle of slide 55. On the right, the sensor with the cloudy biofilm, and on the left, one that's been cleaned with alcohol. And then there's some other strange UV maintenance issues like corrosion on electrical contacts, and we found a nest of ants living in the power supply, and then the lizards and the coqui frogs would go and eat the ants. As you can see, the lizard on the control box, and these coqui are everywhere. They got inside the fan of the UV system and also in our SUV. And when we started up the conventional treatment system, they all came hopping out of the tube settler. Another lessons learned: do not assume that materials will be available on the island. The sand that's purchased comes from Florida, and for the pressure sand filter, we used riverbed sediment that we sieved down and installed. Another lesson learned is don't take electrical power for granted. It's unreliable and expensive, greater than 2 times the U.S. average. Well water pumps in Puerto Rico are not used due to the high cost of electricity. And these are UV study acknowledgements, thanks to the non-process water system operators and Inter-American students. The second study is a renewable energy study that started in 2015. There wasn't enough water for both communities, treated water for both communities. So what we did was combined the water from the lower source with the upper source by installing a solar-powered pump up to an equalization tank at the top of a steep hill, and then a gravity fed into the conventional water treatment system, and then down to the upper tank and to the communities. These are our project and volunteers that would show up on a regular basis on slide 61. And the community was very helpful. They installed a solar powered pump building on top of the tablet chlorinator. We had to look at, determining the elevation change for the pump selection. We've used GPS units, 2 units because of the rainforest canopy, and found a difference of about 350 feet. Here we are installing the solar-powered pump and control cabinet. The control cabinet ensures the operation of the pump regardless of the supply conditions. If there's no flow, or if there's empty or full equalization tank at the top of the hill, and a timer is installed to accommodate pumping at various times during the day. Here we are installing the water lines. There's about 3/4 of a mile of water lines, 1 inch, and we had to connect those to the solar powered pump and the water storage tank. And then we had to roll the equalization tank up the 350-foot hill through the jungle and find a level area to install it. And fortunately, the solar-powered pump worked. It lifted the water up 350 vertical feet, and now it's gravity feeding to the treatment system. So overall, you can see the cost, $2,500. This is without labor. It's a 3/4 horsepower pump, the pump control panel, and then miscellaneous gauges and piping and the equalization tank. So the second portion of the study was the solar power, and one of the major costs for electricity for small communities in Puerto Rico is the transfer, treatment, and distribution of drinking water. As I mentioned earlier, because of the high cost, the communities revert to unfiltered surface water systems, which can create serious public health risks and non-compliance. Many of the non-processed groundwater systems, 141 out of the 242, could use solar-powered pumps to extract and deliver groundwater. The good news about solar is its efficiency has doubled in 40 years, and the prices dropped down to 30 cents per watt. It's actually competitive with onshore wind power as of 2016. A little background on solar panels. The high efficiency photovoltaic cells are typically used by NASA and are not commercially available. The commercially available solar panels are made from mono or polycrystalline silicon and are half as efficient, 14 to 22%. And then the largest solar panel manufacturer companies are based in China, the US, Canada, South Korea, Japan, and Taiwan. In 2016, the US added about 125 solar panels every minute. In 2015, less than 2% of the electricity in Puerto Rico came from solar power, even though they have readily available sun. So the first step was to build a battery enclosure with community help to install the marine cell batteries and the inverter to convert the 12-volt electricity to 120-volt electricity. And then we installed the solar panel frame with 3-inch galvanized steel posts anchored in concrete due to the risk of hurricanes in Puerto Rico. And here we are installing the solar panels on the frame. So all in all, the solar panels cost about $12,000. The most expensive item was the inverter system, followed by the mounting structure, and then the solar panels and batteries. The environmental benefits: the energy produced by the 245-watt system in 1.2 years will offset, or 1.5 years will offset the energy used to produce and install the system in Apiadero. And as installed, the solar panels will eliminate as much greenhouse gas emissions as not burning 3,000 pounds of coal. Atmospheric carbon as is sequestered by 2 acres of forest per year. And then greenhouse gas emissions is not driving 6,600 vehicle miles per year. And this is the solar power study acknowledgements, the people we worked with in Puerto Rico, volunteers, and the solar power company that helped us install them. The final study is biosand filter studies. This is the P3 biosand filter that we installed. We built a concrete pad with a frame. These are 1 gallon per minute slow sand or biosand filters. One of the issues, we wanted them to be gravity feed, and the lower source dam was too low to gravity feed, so we put in a temporary dam above the biosand filters for gravity feed. You can see the original dam up in the watershed, and the dam that we built on the right side of slide 82 with bags of dirt, and then we added concrete after we had established the water line. The biosand filters come UPS. They're very lightweight. They're super sacks. They come in boxes, and then they also ship the underdrain for the slow sand or biosand filters. Then you ratchet the bags up and add the sand. You can see the bulldozer in slide 84. It rained the day we brought the sand down. It tore up the road, so they brought a bulldozer in to make it accessible again. And then the big deal is transporting and filling the bags with 15,000 pounds of sand, or 30 cubic feet of sand per bag. We built a distribution system manifold to control the water level in the 4 biosand filters, and this is at startup. So we did a ripening study. You can see the turbidity was reduced in the first month from 5 down to 0.15, and the E. coli removal was pretty consistent at 4 log removal. We actually hired students on this contract to do the sampling on a regular basis, and after about 1.5 years, the biosand filters degraded from UV, and we bought actually a solar screen at Home Depot and put those above the biosand filters to prevent the UV damage, but it was a little too late. However, we did clean those up and do the study as shown on slide 90. We looked at bacillus, the removal of Bacillus globigii and E. coli in 2 of the filters. We injected the test pathogens into a 5-gallon bucket, and then through a shower head. We had forgotten the shower head, so we made our own out of an Algene bottle, and that's the Schmutzdecke on the biosand filter as you look down on it. And here are the results. You can see 3.5 to 4.5 log removal of B. globigii, and then the 3 to 7 log removal of E. coli. So in summary, the biosand filter results, there are quite a few different local sources of waterborne pathogens. Oftentimes horses or cattle are tied up in the watershed grazing, and pigs have pens, but these goats run wild, and the dogs also move around freely in these watersheds. The second, or the last study is the Citizen Science and Water Quality Monitoring Studies in 2017. You can see some operator training going on in all these small communities are invited to Apidera to learn how to analyze water treatment samples. We installed some source water monitors. You can see a turbidity sonde in the source water that will record the turbidity over time. You can see we installed it in February of 2017, and at the end of April there was a huge storm, and the sediment buried the turbidity sonde, but we got 3 months of data, or 2 months of data at about 4 NTU. We also looked at disinfectant residual in the water storage tanks over time. You can see the temperature varies between 74 and 84 degrees, and as the chlorine is added, the pH drops from using the pH ORP sensor. And while we were doing this, there was a stampede of goats that ran by the storage tank on slide 98. And then the water quality sampling analysis, we worked with volunteers from the community on an IDEX analysis, looking at total coliform and E. coli. We trained the operators and the volunteers and the community members to do their own E. coli and total coliform analysis. As you can see here, with using the IDEX system, we went and collected samples all the way from the source, all the way through the distribution system. The good news, the distribution system samples were very low in E. coli and total coliform. Some of the source waters between EPA and Citizen Science were a little different, but I think those issues can be resolved with better subsampling techniques in the future. And finally, there's Hurricane Maria that hit September 20th, 2017. You can see how large the hurricane is. The little black dot is exactly where our systems are, right in the eye of the storm there. You can see the path of the hurricane on slide 102 with La Sofia and Apiadero shown on the map. It hit the southeast side of the island. And our solar panels at Apiadero survived wind gusts of up to 110 miles per hour. And Maria, as you all know, caused extensive damage to infrastructure, causing a complete loss of communication, energy, and water services. Here's some of the community damage in the areas we were working in. It looked like a completely different place after we came back to visit. These are the water systems. You typically can't see them hidden in the rainforest, but the canopy was completely destroyed by the hurricane, so we actually could see them. Here's another slide showing the canopy before Maria in the shade. We had put the 1-inch pipe through a tree root, and I went up to find that tree root. Fortunately, the tree hadn't come down in the hurricane, but all the other trees around it did. So it kind of shows you how extensive the damage was. In fact, the photo on the left after Maria, that's about 5 foot of vegetation that grew up in about 6 months compared to before Maria, where there was very little vegetation by the tree. There's some of the creepy hurricane vegetation that took over the solar panels and the biosand filters. And then our water systems, fortunately, avoided extensive damage. However, you can see one major tree just missed the package plant, and it's still sitting there, I believe. We're trying to come up with a way to get that down without destroying the groundwater well below it. And I believe a boulder rolled down and hit the concrete wall, causing the damage in the center bottom picture of the slide. And a tree came down on top of the solar powered pump enclosure, but it wasn't damaged. So lessons learned, community involvement and education are critical. If the community does not see any benefit from the water system, they will not take ownership, and payment is difficult to collect. We use local assistance to keep the community involved. The economy is a challenge, and it is amazing what can be constructed in difficult terrain with everyone pitching in. I just want to recognize some of the people that I worked with on all these projects, especially Dr. Graciela Ramirez with Inter-American University, Dr. Melissa Crespo with Inter-American University, Harvey Minig with Inter-American University, Christina Maldonado with EPA Region 2, Rajiv Sinha with Tri-Hydro Corporation in Cincinnati, Ohio, and then all the volunteers and operators, Pedro Silvario, Taina Javier, and Lisa Albanese and Carlos. I think I got everyone, and Dan Williams, and Roy Morrison. So with that, are there any questions?
All right, thank you very much, Greg. Thank you, and thank you for Marlia for 2 outstanding talks on tribal and very small systems, slightly different climates on today's talk, and very enjoyable.